So just as a review, we're going to use the words, the letter in the words tables. So 6 letters without repeating any letters. How many 4-letter arrangements can we make if there are no restrictions? How would I find it? All right. Okay, 4 positions. And I know I'm going to multiply. No restrictions, which means I can start here and work to the right. What would it be? 6, 5, 4, 3, which gives us 31, 23, 60. Okay. Again, we're doing this. We're doing this for all of them. But now we've got a restriction. The word must end in a T. What do I fill in first? The far right? With what number? 1. Okay, because it has to be a T. I've used the T. How many letters are left? And then 4, and then 3. I mean, you could have gone 5, 4, 3 like that too. That still would have worked. But that's going to give you 60. 60 different words. The word must start and end in a vowel. So there's 2 possible ones here. I've used one of the vowels. Where do I go next? The end. And what do I put here? 1. So the 2 vowels have been used up. Okay? Because if you think about it, I could go A-E or E-A. So 2 times 1, there's 2 different possibilities. Now the remaining letters, there's 4 of them, right? So one of the 4 goes there, and then the 3 goes there. And that gives us 24. Only consonants are used. There's 4. So 4, 3, 2, 1, or just 4 factorial, which is also 24. Okay. So those are the kind of questions we've looked at with restrictions so far. But we're going to look at a couple other types. And one is, I know we've done letters and numbers mainly in our problems, but what if letters repeat or numbers repeat? How do we deal with that? So let's consider the 4-letter arrangements using the letters from the word pool. This is a little different because if you notice all the words in the examples we've done to this point, all the letters have been different. Okay. Now, what happens if some of the letters are the same? If they were all different, well, I would simply go, okay, I could put one of the first letters there, and then the next letter, and then the next letter, and then the next letter, or just 4 factorial, which gives me 24. Okay. However, consider this. Call this the I'm going to call this the red O. I'm going to call this the blue O. So it is possible to have this where the first one's red, the second one's blue, or it is possible to have this where the first one is the blue O and the second one. Those are two different arrangements, but it's the same word. So what I need to do is I need to divide those repetitions out. Okay? There's two of them, right? I only, like, that's it. I wrote the word pool. There's two of them, but I only want one, so I cut it in half. Just like another word we could form would be loop. And there's two different ways I could do loop. I only want half of them. Or I divide by 2. So what we could do is just find it as if there's no repetitions, and then divide by 2, because the O's could be arranged in 2 factorial ways. Right? I could go red O, blue O, blue O, red O. Those are the different combinations. So, because I want to use factorials. So what we could do to find it is say, okay, if all the letters were different, I'd just do 4 factorial. But because 2 of the letters are the same, I'm going to divide by 2 factorial. So that gives me 24, divide 2, which is 12. That's a pretty simple example. If there's more than one letter that repeats in a word, we have to divide those away as well. Okay? So the general formula, if we've got n set of objects with A of one kind that are identical, B of another kind, C of another kind are identical, and so on, the number of arrangements, I would take n factorial divided by A factorial, B factorial, C factorial, all being multiplied together. This will make more sense as we look at a couple of examples here, if it already doesn't. So how many arrangements can I make? So if there's 5 letters, I'm looking for 5-letter words. If there's 8 letters, I'm looking for 8-letter words. So if they were all different, automatically, that's how I would find all the permutations or arrangements, 5 factorial. But they're not all different. Right. There's 3 E's. So I divide by 3 factorial. Why? Because there's 6 different ways you can arrange 3 E's, or 3 times 2 times 1. And then you just calculate this, and this actually works out to 20. In aardvark, if they're all different, 8 factorial. But then divide away all the letters that repeat, factorial. So what would I do? 3 factorial for the A's, and then 2 factorial for the R's. So that's the A's, and that's the R's. Just like this one here is the E's. I wonder how many of you could calculate this right now. This would be a calculator question. Do you know where to find all the stuff? Well, the bottom's pretty. 3 factorial is 6. 2 factorial is 2. So the bottom is 12, but 8 factorial, how much? 3,360? No, I want 8 factorial. 40,320, yeah. And then you said it works out to 3,000. Yeah. Okay. So a question like this, if you were asked to find the number weight, this would be a calculator question on the prevention. It could, however, be in the non-calculator section, and you would be asked to leave your answer like this. It would say, find how many different ways, arrangements for aardvark, but leave your answer in factorial form. So then you'd stop here. You wouldn't have to do it.
She took it for her chem exam.
Okay. So doesn't necessarily apply just to words. It can apply to other situations as well. For example, how many 5-digit numbers can be made from these 5 digits? Again, if they were all different, if I'm looking for 5-digit numbers, there's 5 digits, and if they were all different, they'd be 5 factorial. But then I'd have to divide away the ones that repeat. Factorial. Which would be what? 2 factorial times 2 factorial. So that gives me 120 over 4, which is 30. Okay. Another type of question. How many possible answer keys are there on a 10-question true-false test if 5 of the answers are true and 5 of them are false? Remember, you always start with the assumption that they're all different. Say that there's 10 different ways to answer. Over 5 factorial times 5 factorial. And that one is, you could be asked to leave it like that, or you could be asked to find the answer. And what do we get here? You should get 252. Okay. This one's a little interesting. How many paths can you follow from A to B in this grid if you can only move up and only move to the right? Okay. So what I need to figure out is how many moves do I have to make to get from A to B? Pick a path, whatever you want. It's always going to be the same number of moves. So I could go 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 10 moves. If I did a more complicated move, 1, 2, 3, 4, 5, 6, 7, 8, 9, still 10. Doesn't matter what, because remember, you can only move to the right and up. You can't move down or left. So, assuming that they were all different directions, 10 factorial. But in each of the 10 moves, 4 of them are always you're moving up. And 6 of them you always have to move to the right. So think of these, if these were all different letters, the number of arrangements would be 10 factorial, but they're not different letters. There's 6 R's and 4 U's. So I'd have to divide by 6 factorial times 4 factorial. You see the different types of questions that can be asked. Okay. So again, like this would be the total paths. But because to go to the right 6 times, we have to divide 6 factorial away. And because we go up 4 times, we have to also divide 4 factorial away. Okay. So that's repeated letters or digits or paths or whatever you want to call it. Okay? That's one type of restriction we could deal with, situation where we use the fundamental counting principle on factorials. The second main type I like to talk about is certain I know we've already talked about restrictions, but this is kind of like a special case of restrictions. So we've got 5 people. They're seated on a bench. How many ways can they be seated if there's no restrictions? Well, 5 seats. I mean, I don't even have to do this. I could have just done 5 factorial. Okay. And that gives me 100%. A and B have to sit together. They insist on sitting together. Well, again, we're going to have 5 positions. What you have to do is you have to think of A and B like a block. They have to stay together. Okay, so treat them almost like as one seat made up of 2 seats. So they could be here. They could be here. They could be here. They could be here. Let's put them here. So if they're treated as one, that means the total number of people is now 4. So we go 4 times 3 times 2 times 1. Because these guys have to move together. However, within their seating, how many different ways can they be seated? 2 ways, right? A first, then B, B first, then A. Or 2 factorial. So what we would do to find it is we'd say, okay, if we treat A and B as together, we have 4 groups. The arrangements are 4 factorial. Within the A and B group, there's 2 different ways they can be arranged. So I get this. So that gives me what? 48? I think. Yeah, 48. This one, you got to think about a little bit. What if A and B insist that they sit apart?
Putting nice in the park and have one spot. Like first mistake.
That could get a little confusing, right? I'll give you a hint. Use the previous answers. Use A and B. This is the total number of ways they consider there was no restrictions, right? This is if they have to sit together. Wouldn't the difference between them be they're apart? Okay, so we basically take 5 factorial if there's no restrictions, minus if they have to be together. And we've already figured these out, it's 120 minus 48. Which is going to give us 72. So if you encounter a situation where they're apart, find the total, subtract the number that they're together to get the number apart. This last one. A and B must sit together, so must C and D. Don't we have P blocks now? Like A and B have to stay together. C and D have to stay together. So you got to treat these guys like one and these guys like one. So how many different ways can they in this, and this be arranged? 3 times 2 times 1. 3 times 2 times 1. Because these guys could go here, they could go here, they could go here. So these guys can move around too. So we get 3 factorial. How many ways can they be arranged? 2 factorial or 2. You don't even have to write the factorial if you don't want to. It would be 2 times 1. And then 2 factorial again, 2 times 1. So that would give us 24. I believe. Okay. And this. How many ways can 4 married couples sit on the bench if the spouses must sit side by side? Well, how many positions do I have? Total. 8. But then I gotta block them off, right? I gotta do 4 blocks. Which means the blocks can be arranged 4 times 3 times 2 times 1. But within each block, each one can be arranged 2. You can write 2 factorial with just 2. So it's going to be 4 factorial to find the total arrangements of the couples, the 4 couples. And then within each couple, they can be arranged like so. Oh. Got it. So 4 factorial is 24 times, well, That's 16, so 24 times 16 gives me 384. So that's what your test is going to go up to. Okay. And